So far, we've discussed the first of the two primary ways for nucleophilic addition to carbonyls, and those are the irreversible reactions. Another way of classifying nucleophilic addition reactions is the reversible additions to carbonyls. And we base the classifications within this category to be based on the reaction conditions, either acidic conditions or basic conditions. So let's take the first, which are the basic conditions. Under these conditions, we deprotonate a nucleophile to raise the HOMO, and this makes it more reactive. And so let's say we have some carbonyl. Let's say we have a ketone, and we're going to react this with some nucleophile in the presence of a base. That base serves to deprotonate the nucleophile to increase the HOMO so that the nucleophile is now negatively charged. And now it's nucleophilic enough to then add to the carbonyl. And so we get nucleophilic attack of the carbonyl to give us a tetrahedral intermediate. Which then, of course, can get trapped by some exogenous proton source, ammonium chloride, for example. Okay, so the key point here is that the base raises the HOMO. So now the maybe weakly nucleophilic nucleophile can then attack the low-lying pi star CO. So there are a couple of examples of this. Maybe the best example is when we were to take, or if we were to take acetophenone in the presence of sodium cyanide. And so we can think of sodium cyanide as being neutral, but really what has happened here is we've taken HCN and we've added sodium hydroxide, and what happens is the base deprotonates the HCN to give us sodium cyanide plus water. And so now sodium cyanide is deprotonated, and so in the first step we can get nucleophilic attack of the cyanide group onto the carbonyl to give us a tetrahedral intermediate, followed by protonation of that intermediate to give us the product. And so the product in this case is going to be this one, which is what we call a cyanohydrin. Okay. So nucleophilic addition occurs to give a tetrahedral intermediate, which either protonates immediately or reverses if the pK is less than 15. And so in this case, we have to distinguish this from the irreversible reaction conditions. Notice that we have two reversible arrows here, right? So the pKa-H of the nucleophile has to be less than 15, and indeed for sodium cyanide, the pKa-H is 9. And so that's less than 15, and so this reaction is under thermodynamic control. Right? And so these are reversible reactions. Let's take the case of the acidic conditions. And there are many more examples of acidic conditions, but the principle is exactly the same. Under the acidic conditions, we're going to protonate the carbonyl to lower the LUMO. And so unlike in the case of basic conditions where we deprotonated the nucleophile to increase the HOMO, now what we're going to do is to run this reaction under acidic conditions, protonate the electrophile. Now we have our protonated carbonyl, and this carbonyl is now has a lower LUMO. So protonated carbonyls have lower LUMOs. Now this thing could react with an incoming nucleophile. So we can, of course, have a resonance structure here, which sort of indicates why protonation actually works. It works because we're generating now a new positive charge at that carbon. And so now what can happen is a nucleophile that hasn't been deprotonated can come along. It can attack that system. right? So it either attacks there or it attacks there. It can generate a new tetrahedral intermediate. This new tetrahedral intermediate has a positive charge on the nucleophile, and then we simply lose a proton to give us the product. All right, so this is the generic mechanism for this reaction. Now there are three different types of examples of this. The first is the cyanohydrin formation. The second is the Gemdial formation, and then the third is the acetal formation. So we're going to go over the first two in this lecture. So let's talk about first the cyanohydrin formation reaction. So what is a cyanohydrin? A cyanohydrin is a molecule that comes from the reaction between some carbonyl and HCN. And so this is going to give a molecule, a functional group, known as the cyanohydrin. And this reaction is under thermodynamic control. The pKa of HCN is 9.1. And so this is something that's less than 15. So we can say that this reaction is under thermodynamic control because it's reversible. So what is the mechanism of this reaction? Well, we start with the carbonyl. Right, this carbonyl is then going to become protonated by HCN. Lone pairs on the oxygen are going to grab a proton, and that's going to generate a protonated carbonyl, which is much more electrophilic than just a non-protonated neutral carbonyl. So then cyanide, which is a good nucleophile, can come in and it can attack the pi star CO, and that's going to generate the cyanohydrin. Now this reaction is reversible. There's an equilibrium constant associated with it. And so let's take a look at the reaction coordinate diagram for this. We've got some carbonyl sitting maybe right here. We've got protonation of the carbonyl to give us this charged species. And that charged species, of course, is more electrophilic, so it's higher in energy. And then we get funneling into the product, which is the cyanohydrin. Now this reaction is reversible, so we can go in the forward direction, but we can just as easily go in the reverse direction, in this direction. And so there is an equilibrium constant associated with this type of reaction. And so we want to consider what the effect of having that equilibrium constant is. Consider the following two cases. So let's say we have acetaldehyde versus acetone. And each of these is going to undergo a reversible reaction with HCN. And we're going to get, in both cases, a cyanohydrin. And so in the first case, we have a cyanohydrin that looks like this. In the second case, we have a cyanohydrin derived from the ketone that looks like that. So the KEQ, right, for this is 7100 for the case of the aldehyde, and the KEQ for the ketone is 32. And so remember that KEQ is products over reactants. So what we're saying here is in both cases, under these conditions, the product is favored, but the product is favored more in the case of the aldehyde. So why is there this difference? Why is there such a difference? So like most things, there is an electronic rather than steric explanation. So the difference in the stability of the products is roughly the same, right? We basically have all the same types of bonds. So it must arise then from the stability of the starter materials. And so the stability of the starter materials is what's going to drive the equilibrium constant. Okay, so it's going to drive the KEQ. Ketones are more stable than aldehydes. Okay, and so since the energy of the transition state and the energies of the products are about equal, there's going to be a large difference in the reactivity. So let's take a look at what that would look like. So we said that ketones are going to be more stable than aldehydes. So let's draw these two kind of like this. And so the transition state energies are going to be about the same. All right, the product energies are going to be about the same. And so the only difference really here is that we have now a big gap in between the energies of the starter materials. So there's a big gap there, and there's only a small gap here. Okay, so this gives rise to a much stronger KEQ for the aldehyde in favor of the products than it is for the ketone. Ketones are more stable than aldehydes, and since the energy of the transition states and the energies of the products are about equal, there are large differences in reactivity. We don't really care how large that transition state energy is, the activation energy here or here, nor how high these activation barriers are, because we're under thermodynamic control. There's enough energy to overcome any energy barrier. So you might be wondering, why are ketones more stable than aldehydes? And this is due to sigma donation. Electrons like to be spread out, and this can occur more in ketones than it can in aldehydes. So let's take a look at what a ketone might look like from a perspective drawing. And so let's say we've got acetone here. Okay, in acetone, we've got this pi star CO orbital, which is right here. And this pi star CO orbital is overlapping with several CH bonds. Okay, so there's an interaction here and an interaction here. And so we've got 6 sigma CH bonds overlapping with the pi star CO. And so you've got lots of sigma donation happening here. And this delocalization can occur 6 times, which is going to raise the LUMO of the ketone, making it less reactive. And so let's take a look at what that might look like in terms of a molecular orbital diagram. If we have a sigma CH bond overlapping with a pi star CO, and we've got 2 electrons in there that are overlapping and mixing to give 2 new molecular orbitals, what happens is the sigma electrons certainly go down in energy, but the pi star CO goes up. And so this is going to raise the LUMO, and that's not going to make it certainly more reactive, right? It's going to make it less reactive. In the case of an aldehyde, right, we don't have as many sigma donations happening. We only have, let's say in the case of acetaldehyde, 3 sigma donations. Because one of those is a hydrogen, right? And so we've got only sigma donation happening from the bottom side, right there. That can only occur 3 times. And so it's still occurring, but it doesn't occur as much, and so the LUMO is going to be lower. And so this is going to explain why aldehydes are higher in energy than ketones. All right, so what other factors besides sigma donation are going to influence Ku? Well, we can take a look at the following couple of examples. So these are all going to be equilibrium constants, KEQ values, for the reaction of these four molecules with HCN, so the cyanohydrin formation KEQ. Right, so we've got benzaldehyde, we've got acetone, we've got acetophenone, and we've got the pivalyl ketone. All right, and so what are the KEQs here? All right, so the KEQs for benzaldehyde is 212. For acetone, we said it was 32. For acetophenone, it's 0.77. And then for the terbutyl version, terbutyl methyl ketone, it's 0.12. And so in this instance, we need to take a look at a couple of factors. So the difference between acetone and acetophenone, all right? So if we're comparing just these two, all right, we notice that on one side we've got a methyl group, and so that's going to be the same effect. And so sigma donation kind of cancels out here. And so what we're really asking ourselves when we're looking at these two examples is what's the effect of having a methyl group versus having a phenyl group? Okay, so this is the difference between resonance versus sigma donation. So resonance delocalization, as we know, is a stronger effect. And so resonance delocalization is really pi CC overlap with the pi star CO. And if that's a stronger effect, that's going to increase the LUMO. It's going to increase the energy of that pi star CO, and it's going to make it less reactive. And if it makes it less reactive, the KEQ is going to go down. Right, so the difference between acetone and acetophenone tells us that conjugation is more powerful than sigma donation. Delocalization from that pi CC into the pi star CO occurs because these orbitals are closer in energy. There's better mixing. How about the case of terbutyl methyl ketone? And so this is maybe comparing acetone with the terbutyl version. So again, we've got two methyl groups on the right-hand side, which basically will cancel out. So we now want to know what the difference is between having 3 CH bonds doing sigma donation and 3 CC bonds doing sigma donation. So in the case of terbutyl methyl ketone, there's better sigma donation, right? So sigma CC is a better donor. Right, so sigma CC is a better donor than a sigma CH due to better orbital overlap, right? It's just a little bit bigger, a little bit longer, and so you get that, that pi star CO increases in energy. And in addition to that, there's a little bit more steric crowding. Right, so it's much more difficult to access the pi star CO, right, because you've got this big, bulky terbutyl group on the outside. Okay, and so again, if we're looking at the differences between these, we notice that the aldehyde is going to be is going to have the highest KEQ because it doesn't have that sigma donation as much. It doesn't have the overlap as much, and so if you're comparing benzaldehyde to acetophenone, so this is the same in the case of benzaldehyde and acetophenone, so the resonance cancels out, and so now we're left with a CH, which cannot participate in sigma donation, versus a CH3, which can, and of course CH3 is going to increase that LUMO, and so of course aldehydes are more reactive than ketones. Okay, so that's the cyanohydrin formation reaction. Let's talk a little bit about the next type of reaction, and that's the Gemdial formation reaction. All right, so Gemdial formation, a geminal carbon means same carbon. And so what you have here is you have a diol in which you've got two alcohols on the same carbon. And so we can write this out as follows. So if we take this aldehyde, this ketone or aldehyde, and we react it in the presence of water, we can get what's known as a Gemdial. And so this Gemdial looks like this. So we've got two alcohols attached to the same carbon atom. Now this is a very slow reaction. It can be accelerated by either acid or base catalysis. It turns out that heat will favor the reverse direction because entropy is going to favor a bimolecular set of products. But there are similar effects on KEQ that we had for the cyanohydrins. And so let's take a look at those. So let's have acetone. Let's have trichloroacidaldehyde. Let's have formaldehyde. And then let's have hexafluoroacetone. And so what's the KEQ going to be for these reactions? In the case of acetone, it's 0.02. Okay, in the case of trichloroacidaldehyde, it's 2.7 times 10 to the fourth. In the case of formaldehyde, it's 1,000. In the case of hexafluoroacetone, it's 10 to the sixth. Okay, so how can we explain these KEQ values? Well, we can see that in the case of acetone, right, we've got sigma donation. That's going to increase the LUMO. If we compare that one to hexafluoroacetone, we can see that there's no longer sigma donation happening. What's happening now is that you've got some really electronegative fluorine atoms that are going to pull electron density away from the central carbon atom, and that's going to lead to an even greater positive charge on that carbon. So this is going to increase the electrophilicity of that carbon atom, and it's going to increase the KEQ value. This acetone, you might be thinking, well, it's a ketone. Why is it higher than the aldehydes? Well, that's because it's got 6 fluorine atoms on it. But if you were just to compare the two aldehydes, the formaldehyde and the trichloroacidaldehyde, you would see that this is also pretty consistent, right? So you've got some really electron withdrawing chlorine atoms, electronegative atoms that are pulling electron density away from that carbonyl. That's going to lead to even greater positive charge and increase the KEQ value. And of course, if we compare the formaldehyde versus acetone, we can see the effect of sigma donation here. Now, one thing to note about this is that you cannot buy formaldehyde by itself. So you need to buy it in a few different ways. It's either a 40% solution in water. You can buy it as a substance known as paraformaldehyde, which is really just a polymer of repeating CH2O units. Or there's a substance known as S-trioxane, which has units of CH2O embedded within a 6-membered ring. So there's 3 oxygen units embedded within a 6-membered ring. So these are good sources of formaldehyde. Now, how can we get Gemdial formation with acid or base catalysis? Well, let's try base catalysis. All right, so under basic catalysis, right, we've got some base that's going to react with water. That is going to give us deprotonation to give us protonated base plus OH minus. The other way this could happen is you could have a anionic base reacting with water to give you a neutral base plus OH minus. Right, so again, what's happening here is that your nucleophile, right, has a arrays HOMO. Right, water's not a good enough nucleophile to attack the pi star CO, so its HOMO, its non-bonding pair of electrons on oxygen, is much too low. But we can raise this HOMO by deprotonation. And so common bases that we can use here are things like potassium carbonate, triethylamine, and sodium hydroxide, potassium hydroxide. Okay. And so we can draw a mechanism here. So we've got, let's say, our generic ketone. We can react it with potassium carbonate and water. Right? That's going to give us, according to the mechanism above, OH minus around. This OH minus is going to attack the pi star CO. That leads us to its tetrahedral intermediate. So you've got now a new carbon-oxygen bond. We've got an oxygen with a minus charge on it. Notice all of these reactions are reversible. We can get then the anionic intermediate can attack the water again to regenerate OH, and so OH minus is truly going to be a catalyst here. We can go back to the beginning and do the reaction all over again. Now, under acid catalysis, we have a ketone or aldehyde is not really a good enough nucleophile to react with the non-bonding pair of electrons on the incoming water, right? So its pi star CO, its LUMO, is too low. But we can lower the LUMO by protonation with a Bronsted or a Lewis acid. And so we can do this with the generic electrophile, aldehyde or ketone. We're first going to protonate. This protonation lowers the LUMO enough so that water can attack as an incoming nucleophile. Right, so now the non-bonding pair of electrons on oxygen are nucleophilic enough. We're going to generate this tetrahedral intermediate, where now we've got a new carbon-oxygen bond. Water is still protonated. And then we're going to deprotonate water, loss of a proton, to give us the Gemdial. And again, our proton source is a catalyst. It can go back to the beginning and do the reaction all over again. And so this is a Gemdial formation. It can occur under acidic or basic conditions. Let's consider the following reaction and see if we can determine why this reaction goes the way it does. And so let's say we have some labeled acetone. And so we have, let's say, O16 labeled acetone. And in the presence of O18 labeled water and hydrochloric acid, the product we get is full incorporation of O18 labeled acetone. Okay, so how does this reaction work? Well, we're going to undergo a mechanism that proceeds through the Gemdial intermediate, but then remember that we can that this reaction is reversible, and so we can proceed in the reverse direction by what's known as the law of microscopic reversibility. And the law of microscopic reversibility states that the series of arrows in the reverse direction will be opposite the arrows in the forward direction. For a reversible reaction under thermodynamic control. Okay, and so let's try to draw the mechanism of this reaction. Right, so the first thing that's going to happen here is we're going to protonate that carbonyl. Right, so we're going to take the lone pairs on oxygen, we're going to protonate because we're under acidic conditions. Right, so HCl is a source of H+. That's going to give us a protonated O16 labeled carbonyl. Then we can get the O18 labeled water to attack that carbonyl. And so that's going to give us an intermediate. And so let's make sure we keep track of our oxygen 16 and our oxygen 18. Right? So our oxygen 18 is the new bond that's formed. It's got a positive charge on it. In the last step of that Gemdial formation reaction, we lost a proton. And so then we have this carbonyl here, or this Gemdial here, excuse me. Right, so this Gemdial is here, and let me just clean this up. This is going to be no longer R groups, but it's just going to be acetone groups, methyl groups. Okay. Now, at this stage, we have the Gemdial, but remember, we can go in the reverse direction. But if we go in the exact reverse direction, in this way, we just end up with O16 labeled product. What would happen if we went in the reverse direction, but now formation of the O18 labeled acetone? Right, so let's try to go in the reverse direction. So in this last step here, what we did was we lost a proton from O18 labeled water, O18 labeled alcohol. What if we were to think about protonating the O16 labeled water? That should be the exact opposite of deprotonating O18 labeled water. And so again, this is the law of microscopic reversibility. And so we can draw out the product of this. So the product of this step is we've got now O16 labeled alcohol, protonated alcohol. The reverse step here, going in this direction, would be to take the reverse of water attacking the carbonyl would be water being released from the carbonyl. So let's take our lone pairs on oxygen, kick them down, form a double bond, and release water. So then we have protonated O18 labeled carbonyl plus O16 labeled water. And then, of course, we can remove a proton, which is the last step here. So the reverse direction here would be loss of a proton instead of addition of a proton. And so we can take that proton, slop it off, and then we have our product, O18 labeled acetone. Now, why does this work? Now, the reason why this works is because the small amount of O16 labeled water that you generate will never be able to compete with the water that you have that's O18 labeled, which is solvent. So the reaction is pushed towards the right. And it's pushed towards the right because the law of microscopic reversibility states that the last three steps are just the reverse of the first three. Right? So we can take a ketone, make the Gemdial, but then we can take the Gemdial and form a different kind of ketone that has a different label in it. And so being comfortable with the forward and the reverse directions of these mechanisms is really important as we get to the next type of reaction, which is the acetal formation reaction in the next lecture.